Alright, so following up with our last topic on specific heat, we'll look now at energy and matter with respect to energy and nutrition. It shouldn't be too big a jump to use the term calorie from our last topic in calorimetry and specific heat to think about how calories relate to food calories, which, if you recall from the first lecture in this chapter, we said is a capital C as opposed to lowercase c that we used in the last subtopic. Okay, so if you noticed, I just dropped the term calorimetry, so I guess we should probably talk about what a calorimeter is, because calorimetry is the determination of calories or heat energy by the use of a calorimeter. So a calorimeter is used to calculate the energy value of food, or really any chemical substance. We talked about stored chemical potential energy in those bonds, and so calorimeters are one way that we're able to ascertain the energy value of a substance. So it contains a reaction chamber and a thermometer and some sort of heat sink, which is typically water. Water is cheap and readily available and actually has a very high specific heat, which makes it ideal for this sort of work. The temperature change in the water is related to how much heat energy is given off by the substance. So we're following that reaction by looking at the temperature increase of the water, and therefore we can figure out how much heat was lost by the food that was burned, oxidized in that chamber through a very sophisticated ignition system that typically involves some sort of thread-like substance that's already been calculated, so we don't have too much heat from the food. We take into account that thread burning has its own a little bit of heat, or sometimes it's just an electrical wire setup. But it's very nice and relatively inexpensive method for determining the calorie value of a fuel, or in this instance a food, which is a fuel for us animals. Okay, so we did talk about this, if you remember back a few subtopics, but this is the difference between the capital C calorie and the lowercase c calorie. So in the US, on nutrition labels, we tend to report food calories, which are capital C calories, which are really kilocalories to us scientists. So in science, when we use the calorie, we use the lowercase c calorie. So the capital C calorie is 1,000 of those lowercase c calories, or 1 kilocalorie to us. And therefore, of course, one lowercase c calorie would be 4.184 joules. So therefore, one food calorie would be 4,184 joules, or 4.184 kilojoules. So just to give you a ballpark figure, and especially if you're lucky enough to find a food label that's for a food sold in the US and in Canada or in Mexico, for instance, you'll see both calories and kilojoules listed. So that's very nice that you'll see the difference by a factor of 4.184 times the calories, food calories, capital C calories, to get the kilojoule value. Okay, so if we take a look at your table 2.9 from the text, we typically think about three classes of macromolecules that we consider for food energy, and these are the carbohydrates, fats, and proteins. Carbohydrates and fats are typically used as fuels for the body. Proteins we don't often break down. Hopefully our body can break them down partially to reuse them, but when you start burning protein for food calories for as a fuel, things get a little messy. It's not as nice and clean as carbohydrates or fats. So that's undesirable, but it does happen sometimes for various reasons. So if we look at the food calorie content, kilocalories, which are those capital C food calories per gram, those are what you're typically used to seeing. 4 for carbohydrates and proteins, and then 9 for fats, much higher energy storage molecules, and therefore desirable for that reason if you need high energy molecules, but undesirable because those fats, at least in the modern American diet, tend to accumulate on our bodies as body fat, and that's not so good for our health. But you can see the kilojoule per gram values are just 4.184 times those other values, the kcals or food calorie values. Okay, so there we have it. You also have to be careful, as we said, the calorimeter burns everything. So even things like fiber, which are carbohydrates, they don't tend to get burned in the body. Fiber tends to pass through the system, tends to help as roughage, keep the system operating correctly. So you have to be careful because there are calories that are given for the carbohydrates that include the fiber that doesn't get broken down. So it's a bit of a false advertising, but again, that's the way it's done because in the calorimeter, the fiber burns just like everything else. And so we have an image on the right-hand side that's representative of what you might find on a food nutrition label. And notice the caloric values there are typically for one serving, and we have both calories and kilojoules listed, and not only total calories, but also calories from fat in particular, which are again, things that we want to try to limit in our diet in modern American culture. Thousands of years ago, evolutionarily speaking, we needed lots and lots of fat because we didn't know when our next meal was coming, but nowadays we eat pretty regularly. Most of us eat a little too regularly, and we don't need to have so much fat in our diet. All right, and you see there's that dietary fiber less than 1 gram. So the additional energy that's given for burning that fiber is usually pretty small, but if you have a high fiber food, then the calories are probably a little misleading because you wouldn't burn all of those carbohydrate values, especially the dietary fiber that passes through the system unused. Okay, so there we have a typical food label, and again, hopefully you've seen these many times. If you haven't been reading them, maybe this will be the course that stimulates your interest and you start to read your food labels like I know I do. Here we see table 2.10 that has the general composition and energy content of some common foods, and you notice depending on the food, look at the very first example. The banana there has lots and lots of carbohydrates, very little fat, little protein, and overall not too many calories. If we look at the next entry, the beef, we've got roughly twice the calories of that banana with essentially no carbohydrate. All of that is fat and protein. So again, that protein is good for us, but the fat there on that ground beef is probably a little high. Hopefully you could opt for a leaner cut, get still all that protein and not so much of the fat. And then we have a number of other things listed. Interestingly, if you go for the milk toward the bottom there, we have the full fat, roughly 4% fat in cow's milk, versus the non-fat. There's a huge difference in terms of the fat grams, right? You go from 9 grams of fat per serving to 0 without sacrificing any of that protein. So you have the same carbohydrates, you have the same protein, you've just essentially skimmed off all of that fat, which is why non-fat milk is sometimes called skim milk, and it's roughly half the calories. So if you can make that transition, if you're drinking whole milk, it's probably going to be a tough transition to make, but maybe step down to 2%, then 1%, and maybe finally get yourself to skim, and you'll save a lot of calories and still capture all that protein that you're after. All right, so let's try a problem. If we look at this example, we have a 4-gram sample, 4.0 grams, for those of you who are watching your sig figs, which should be all of you. So 4.0 gram sample of fat was combusted in a calorimeter, and 164 kilojoules of heat energy was absorbed by that water in the calorimeter. Calculate the energy value of the fat in kilojoules per gram. So to solve this thing, we need to consider that 164 kilojoules was produced by the combustion of 4.0 grams of fat. So we can calculate the energy value using the equation below that says the energy value of the fat equals the total heat released by the fat and therefore absorbed by the water in the calorimeter, divided by the mass of the sample. In this case, that's 164 kilojoules of heat released divided by 4.0 grams. Again, it's a division, so we've got our sig fig rule that says the smallest number of sig figs in our values there is going to give us our final number of sig figs. So the 4.0 grams, just 2 sig figs, 164 kilojoules rather, 3 sig figs, so we get a final answer of 41 kilojoules per gram, 2 sig figs based on the mass, and there's our heat energy value, and that correlates pretty well. If you recall, it's about 9 kilocalories per gram, and then when we multiply it by the 4.184, we end up with something roughly in the 40 kilojoules per gram value. So it makes sense. It's an indication we did it correctly, and hopefully it wasn't too difficult for anyone out there to follow. Okay, so talking about nutrition, let's think about the energy requirements for all of us, right? Each of us probably has different requirements, right? We probably each have a different age, gender, level of physical activity. So you need to find a balance that's right for you. If you're like me and your food intake exceeds your energy use, then unfortunately you're going to be in the gaining weight column. If, on the other hand, your food intake is less than your energy use, then you would tend to lose weight. It's a lot more complicated than that. There's all sorts of brain behavioral issues involved. Certain people do have just a low metabolism, and it's very tough for them to lose weight. Other people are blessed with very fast metabolisms, and they might have trouble gaining weight if they want to do so. So it's a little more complicated than this, but the basic science holds that if your calories in are equal to your calories out, then you'll maintain a steady weight. If the calories in are greater than the calories burned, then you'll gain weight, and if the calories in are less than the calories burned, you'll lose weight. And we see some table 2.12 gives us some energy values for some activities. Unfortunately, my favorite activity there, sleeping, has the lowest energy expended by the average adult. So hopefully you're into things like swimming and running versus my activities of sitting and sleeping. Okay, so before we leave our final subtopic here for Chapter 2, let's have one final learning check. So if we have a cup of whole milk that contains 12 grams of carbohydrates, 9.0 grams of fat, and 9.0 grams of protein, how many kilocalories, or food calories, capital C calories, does a cup of milk contain? And we'll round to the nearest 10 kcals. We won't pay so close attention to the sig fig rules, although of course 12 grams of carbohydrate, 9.0 grams of fat, 9.0 grams of protein, we should end up with 2 sig figs in the end, but let's just go ahead and round to the nearest 10 kcals to see if the answer choice A, 50 kcals, or 50 capital C food calories, B, 80 kcals, or C, 150 kcals is the correct answer. So if you haven't already solved this, pause the video here and then start it back up, and we'll see how you did. Okay, so this relied on you remembering back a few slides ago that fats had 9 kcals per gram of heat energy, and carbohydrates and proteins each had 4 kcals per gram, so that you could figure out for each of those components how many kilocalories would be stored in that food. So in this cup of milk, those 12 grams of carbohydrates, we'll have to multiply that by the 4 kilocalories per gram to get a total of 50 kcals of energy from the carbohydrate. 9.0 grams of fat times 9 kcals per gram for the fat gives us 80 kcals. And then finally, the 5 grams of protein times the 4 kcals per gram of protein gives us 20 kcals for the protein's contribution, for a total kilocalorie value of 150 kcals. So answer C was correct, and it did turn out to have the 2 sig figs that we would expect. So there you have it. Hopefully it was easy and straightforward. If you just got caught up in forgetting to look back at the 4 kcals per gram for carbohydrates and proteins, 9 kcals per gram for fat, but now it all makes sense, that's fine. If you're totally lost, go ahead, try some end of chapter problems, and get in touch with me if it's still not making sense, because we certainly want you to be in a situation where you could solve a problem like this should it arise on the exam. Okay, so that does it for Chapter 2. Looking forward to having you join me again for Chapter 3.